In the world of organic chemistry, millions of reactions occur every second. While they may seem complex, almost every reaction falls into one of four fundamental categories. Let's break down the Big Four that govern how molecules transform. Audio equals welcome back to chemistry with Harshada. Right now, millions of organic reactions are firing off every single second, fueling everything from the medicine you take to the life in your cells. It looks like chaos, but there's a hidden order. Almost every chemical transformation on Earth follows one of four ultimate blueprints. Today, we're cracking the code on the Big Four that govern the world of organic chemistry. First up, let's look at addition reactions by examining the mechanism of a hydrogen halide adding to an alkene, specifically, ethene reacting with hydrogen bromide. Step 1. The setup. We start with a simple ethene molecule, characterized by its carbon-carbon double bond, and a molecule of hydrogen bromide. At this stage, they are simply in close proximity. Step 2. The attack. As they approach, the electron-rich double bond in ethene reaches out to attack the hydrogen atom in hydrogen bromide. This causes the double bond to break and the H-bridge bond to snap, leading to a temporary transition state. Step 3. The intermediate. This creates a carbocation, a positively charged carbon atom. Notice how the hydrogen has already attached to one side. Meanwhile, the bromine has become a negatively charged bromide ion, acting as a nucleophile. It's now ready to attack that positive center. Step 4. The final product. In the final step, the bromide ion successfully attaches to the remaining carbon. The result? We've transformed our starting materials into bromoethane. As you can see in the chemical equation at the bottom, the double bond is gone, replaced by two new single bonds. The key takeaway: in an addition reaction, two molecules combine to form a single, more saturated product. Next, let's explore substitution reactions. Think of this as the exchange, or replacement, reaction of the organic chemistry world. It's a bit like trading partners on a dance floor. See the reactants. On the left, we have our starting materials, a chloromethane molecule and a hydroxide ion. The hydroxide ion is our nucleophile. It's looking for a positive center to attack. Let's see the mechanism SN2. This specific example shows an SN2 mechanism. This is a single concerted step, meaning everything happens at once. As the hydroxide ion approaches from the opposite side of the chlorine, what we call a backside attack, the reaction enters a high-energy transition state. In the transition state, look at the center of the image. In this fleeting moment, the bond between the carbon and the incoming hydroxide is halfway formed, while the bond with the chlorine is halfway broken. The molecule is literally in the middle of a swap. See the final products. Finally, the chlorine leaves entirely as a chloride ion, and we are left with a new molecule, methanol. If you look at the final product on the right, you'll notice the atoms have swapped places, but the total number of bonds remains the same. The key takeaway here is simple: one atom or functional group is swapped for another. The partners change, but the dance continues. Let's see elimination reactions, specifically the dehydration of ethanol. Our goal here is to transform a simple alcohol into an alkene by removing a molecule of water to form a carbon-carbon double bond. Step 1. Reactants and protonation. Let's start with our reactants. We begin with an ethanol molecule CH3CH2OH. Notice the O-hydroxyl group? To get the reaction moving, we need a catalyst, typically sulfuric acid H2SO4, and heat. In step 1, the acid provides a proton H+, which attaches to the oxygen. This is called protonation. It turns that poor leaving group O into a great leaving group H2O. Step 2, the transition state. As we move into the transition state, the water molecule leaves, creating a carbocation intermediate. Look at the center of the graphic. You'll see the positive charge on the carbon atom. Because this specific rate-determining step involves only the ethanol derivative, we call this an E1 mechanism, or unimolecular elimination. The rate law is defined by rate equals K, ethanol. Step 3, deprotonation in products. Finally, in step 3, a base in the solution like water or the conjugate base of our acid removes a neighboring hydrogen atom. This is deprotonation. As that hydrogen leaves, its electrons collapse toward the positive center to form the double bond. And there we have our products. We've successfully produced ethene C2H4 and a byproduct of water H2O. Pro tip here is by using acid and heat, we've shifted the bonds, conserved our atoms, and moved from a saturated alcohol to an unsaturated alkene. Simple, elegant, and essential for synthesizing larger organic molecules. Now we're exploring rearrangement reactions, specifically the 1,2-methyl group shift. The goal here is simple but critical: transform a less stable secondary carbocation into a much more stable tertiary carbocation. Step 1: Reactants and formation. Let's look at our reactants. Under specific conditions usually involving acid, heat, or light, an intermediate secondary carbocation is formed. You can see the positive charge on a carbon atom that is only connected to 2 other carbons. In the world of chemistry, secondary is okay, but tertiary is much better. Step 2: The transition state and migration. This brings us to the transition state. This is where the magic happens. A neighboring methyl group CH3 highlighted in yellow literally migrates from one carbon to the adjacent positively charged carbon. This is the 1,2-methyl group migration. Because this internal shift depends only on the concentration of the carbocation itself, it follows a unimolecular reaction order, much like an E1 mechanism. Step 3: Products and stability. Finally, in step 3, we reach our stable carbocation formation. Look at the product on the right. The positive charge is now on a carbon atom surrounded by 3 other carbon groups. Why does this happen? Look at the stability chart at the bottom right. Tertiary carbocations are significantly more stable than secondary ones. Nature always seeks the lowest energy state, and this shift is the most efficient way to get there. Here pro tip is: by moving just one methyl group, the molecule creates a more substituted, stable intermediate. The atoms are all still there, but the new arrangement makes the molecule far more ready for the next step in a chemical synthesis. By recognizing these 4 patterns, you can predict how even the most complex organic molecules will behave. Master the movement of electrons, and you master the reaction. If you found this helpful, don't forget to like and subscribe for more deep dives into the molecular world. See you in next video. Happy learning chemistry with Harshada.